I've started the recording and I'm going to share my screen. Sorry, my voice is a little quiet today. If you can't hear me, please feel free to turn your volume up or just let me know, okay? Okay, so we are starting a new chapter, the derivative. Instantaneous rate of change, right? That's our first thing. A derivative is slope of a tangent line, the instantaneous rate of change in something. There's two different, characterizations of what a derivative is. A derivative is both of those things, okay? Sort of like different perspectives. If you think about it from the perspective of like, what is the function? Is it like a velocity function? Is it a function that's telling you the position of an object? Is it the function that's telling you the temperature of something? Is it a function that's telling you the amount of profit your company gets for, based on the amount of production you do? Is it a function that tells you whatever, right? If you think about it from that perspective of like, what is the function telling you? Like what are the units involved and what are you using it for? Then I think instantaneous rate of change is the best notion of what a derivative is, right? But if you think of a function as a graph, right? If you think of a function as just like, oh yeah, it's just a graph on an XY plane, it does something like that. Then from that perspective, it's the slope of the tangent line. The point. Okay. In either case, we define the derivative the same way. There's kind of two ways to do it. Oh, and there's a special notation. F, and then this little apostrophe, tick mark, we call that prime. Okay. In mathematics, this mark, it's not like a number one. It's more like when I'm typing it, I type it as an apostrophe. That is spoken, F prime of A. That's how you say that out loud. And it means the derivative of F at the X value A. So that would mean the slope of the tangent line to the graph at A, or the instantaneous rate of change in the function at A. Right, so that's our new notation that we're going to use. So there's two ways to define this. Oops. One of them is, well, they're both going to be the limit of the change in y over the change in x as the change in x approaches 0. They're both that, but the way we write that is slightly different. Okay, so first, you could write the change in y as like, well, okay, so the first one is kind of based on this idea that got your like tangent line at some specific point. There we go. Right, that's like A. And then you also have this like other point on the line somewhere at a value, which we'll just call X. And remember, the way we do this is to imagine making a secant line. Remember that? You make a secant line, and then that's what the change in y over change in x is doing. The change in y here over change in x that's calculating the slope of the secant line. And you only get the tangent line when you do the limit of that. Okay. So the first version of the derivative definition involves this a and x. And what you do, switch to black here. What you do is you do f of x minus f of a. That's the change in y. That makes sense that that's the change in y, because it's the change, the difference between the function output values, divided by x minus a. And x minus a is the change in x, right? Now, what we want to do is take a limit of that as the change in x approaches 0. But what that means, what we really want to do is if our goal here is to get the derivative at a, meaning the instantaneous rate of change or the tangent slope at a, what we've really got to do is keep a fixed. A is not going anywhere. A's got to stay right where it is, right? But what you need to do is take x and move x towards a, right? So x gets close to a. What you're doing is you're taking a limit as x approaches a. All right. So I think it might be worth just opening up this Desmos demo again. To say, hey, if you want to know the tangent line here, see this red line? This red line is our tangent line. What you do is you have a fixed, and you take your x value here, and you take your x value and have it approach a, right? And get closer and closer and closer and closer to a. And this dotted purple line, that's the change in y divided by the change in x, right? That's the f of x minus f of a over x minus a, that thing, okay? That is approaching a right here. And as it gets closer and closer to a, the slope of that secant line approaches the slope of the tangent line, right? It'll never actually equal the slope of the tangent line, because when x and a are equal to each other, you have a problem, right? When x and a are actually equal to each other, you have 0 over 0, right? So that's why it's a limit, right? We have all our tools, all our limit solving tools to use there, all right? But I just wanted to, point out, like, that's what this is. That's what this is here. This is coming at it from that idea of you got your x and you got your a, and the x is approaching a. All right. So that's one way to define f prime of a, right? The derivative of a function at a specific point. The other way to do it is a little bit different. In this version, still got our a. We've still got our second point, our imagined second point over here, okay, with the secant line. But instead of focusing on the x coordinate over here, what we do instead is we think about the distance between these 2 points. And that distance right there, we call that delta x, or actually in our textbook we're using, we call it h. So I have gone back and forth over the years and whether I like to use delta x or h. I have settled on using delta x. I prefer to use delta x because I think that delta x is more directly reflective of what it means. It's the change in x. And the purpose of, I mean, the only reason to use the letter h instead of delta x, I mean, and I don't know why the heck it's h. It's just h. It's just, I don't know. Somebody just decided that h was an appropriate letter to use for this. I don't know. But the reason, the only good reason to use h instead is because it's a single symbol instead of like two symbols put together. I don't know. So our textbook uses h, but I'm going to use delta x because I just think delta x is a little bit better. Okay, so if you like, we can write it both ways. So here's the alternative way to set it up. We have to set it up in terms of a and delta x instead of a and x. So when I basically have to write the exact same thing as up here. Okay, f of something, basically f of x, except I can't use x. I don't want it to be in terms of x at all. I want it to be about a and delta x. And the way you do it is you say a plus delta x. And this delta x in my picture over here, by the way, delta x can be negative. In my picture right here, delta x is probably negative because it's like going to the left. Okay, so delta x, you don't want to exactly think of it as a distance. I said distance earlier, but that's like not quite the right idea because we want to say if it's a positive delta x, we're over on this side. If it's a negative delta x, we're over on this side. Okay, so it is like a number that you add to a to sort of change it either by shifting it left or shifting it right. Does that make sense? So what we write here is a plus delta x. We don't have to write minus because if delta x is negative, it'll be minus. Okay. So we've got that takes the place of f of x, and then we subtract f of a. And then we can do the same thing in the denominator. In the denominator, if we replace x by a plus delta x and then subtract a, what we actually see happening down there is that the a's cancel out, right? You see that? Which means that what we actually have in the denominator is just delta x, which makes sense. That's what we should have in the denominator. That's what we had in the denominator originally, right? So yeah, that's what this was. This was supposed to be the change in x anyway. So yeah, so we're back to just having, this is like kind of like back to where we started. We're back to having just regular delta x in the denominator, which is good. So there we go. So that is the alternative way to do it. Now, actually moving forward, this will end up being the main version we use. Okay, they're equivalent to each other. You can use either setup. They're both fine. But the second one is the one we're going to use more often moving forward, and there's a very good reason for that, which doesn't really come up until 3.2. And also I'll hold off on that. Okay, but that's what we're going to use. So now I want to introduce some vocabulary. Both of these are referred to as the limit of the difference quotient.
Tristan?
Julia, yeah?
I have a question. So you say delta x, is it the point or is it the change in between a and x?
It's the change.
Change between the two?
Yes.
Okay, thank you.
But bearing in mind that it's actually the change is is a great word to use actually. Change is better than distance between them because distance between them is what I said before, and that's like distance seems like something that should be positive, but the change in x is what it really is, and that can be positive or negative.
Okay.
Thank you. Okay, so this is the vocabulary we use, but these are both limits, right? So the limit of that part makes sense. The word difference quotient right here. This is the difference quotient, or this. They're the same. They're just two different versions of the same thing. But that's the difference quotient right there. Okay. It's just a slope formula, is what it is. Difference quotient is just basically a fancy word for a slope formula. Okay, and the reason it's called difference quotient is because it's a quotient. Quotient means divide, like the result of division, right? And so basically quotient means like a fraction. So it's a fraction, right? That's why it's called a quotient. And then the difference quotient, it's called, the difference refers to subtraction, right? Difference is the result of subtracting. And they're both, numerator and denominator are both the result of subtracting two things, right? Because they're both the difference in y's divided by difference in x's, change in y divided by change in x. Yeah, so that's just fancy words that you'll hear sometimes. And this all together is called the definition of the derivative of a function at a point. So let's go ahead and do an example. Let's say that let's take a function. Let's take like x squared plus 4x. And let's pick a value. A equals, somebody give me a number. Preferably not something messy. Let's take it like an integer, positive or negative.
3.
Not 3. There we go. Thank you. A equals 3. Okay, so now what we're going to do is we're going to compute f prime, the derivative of the function at 3. Okay, so we can use either of these two. Do you folks have a preference about which of these we use? Number 1 or number 2?
Can we use number 2 since you said that's what we use the most?
Yeah, good idea. So what we want to do is we want to set up the limit as delta x is approaching 0. Did I remember to write that on the previous page? Oh, no, I didn't. I forgot to write that. Oh, my goodness, that's important. Delta x approaching 0. That's the other big difference between these, right? This one's with something, this one's a limit at 0, whereas this is like x approaching a. So that's a big difference between them two. So if we're doing the 0 one, delta x approaches 0, we're going to have to do f of 3 plus delta x minus f of 3 all over delta x. Like that. So that is the setup. Now, what we've got to do is use the delta x, use the f function that is given right here, right? So what I want to do is I want to take 3 plus delta x, and that is going to replace x in my function. And then the result of all of that is going to go, let me kind of put it in like a square bracket. The result of all of that is going to go in this position right here in the expression. This is a part that people have a lot of trouble with for some reason. It's just, so it's basically something you did learn in pre-calculus. It's basically just evaluating a function with some sort of algebraic expression as an input. Or another way to think of it is it's just composing functions together. You have your f function and you're sticking the function 3 plus delta x inside of it. So it's like function composition. But for some reason, it just kind of, it's sort of like this mental gymnastics, which is a little hard to handle. So here's my recommendation. My recommendation is to look at the numerator and see, okay, we're going to have a big chunk of stuff here, which represents f of 3 plus delta x. And what I want to do is I want to write out the entire f function, but wherever there's an x, I'm just going to put a blank pair of parentheses. So like a x squared plus 4x, like that. And then inside that pair of parentheses, I will put whatever is written in here, the 3 plus delta x, like that. So this is my favorite approach. Use parentheses. You will find that on rare occasions, the parentheses are unnecessary and you can just immediately get rid of them afterwards. But most of the time, you need the parentheses there. So like, for example, in this case here, we really need these parentheses here because we're squaring the entire thing, right? And if we're squaring the input, we got to put parentheses around it because the input is 3 plus delta x, right? It's two things added together. So enclose those, you got to enclose those in parentheses to say square the whole thing. And same right here, we really need these parentheses because we're multiplying this input by 4. And if the input is two things added together, you got to put parentheses to indicate that the multiplication needs to distribute across the addition, right? So that's what I said. Very rare, on rare occasions, you don't need those parentheses, but in most occasions, in most situations, you actually want them to be there anyway. So you might as well, that's why I like starting with putting the parentheses in place of wherever the x is, and then stick the input into the parentheses. And then that's just the first one. Okay, so then we're going to subtract here, right? That subtraction, this subtraction is this subtraction. Okay. And then we're going to do another, and then we're going to do it again, but the second time it's a little easier because now I'm just doing it with f of 3. So I can do x squared plus 4x, and I'll take my 3 and put 3 in there like that. Okay. So there's my whole numerator. Now my denominator is delta x. Let me pause. I want to make sure everybody's comfortable with what you're seeing here. I guarantee you the vast majority of mistakes in doing a problem like this occur in this setup. After this, it's just algebra. We've already practiced how to do the algebra. Most of the mistakes happen like right here, just like plugging in the numbers wrong, basically, using the function incorrectly, misinterpreting the notation, all that kind of thing. So do folks have any questions about what you're seeing here at the moment? Here's a question for you. Are these parentheses, these green brackets that I'm using like parentheses here, are these necessary?
No.
Not really. I agree. What about these ones? Are these necessary?
I think those ones are necessary
Why are they necessary, Julia?
because you're gonna have to, like, the negative 3 squared will be 9, so you gotta put the negative in front of it, and 4 times 3 will give you a 12, and then times the negative sign, since they're in brackets, they'll give you a negative 12.
Yeah, it's this negative. This negative here is the reason it's necessary, right? If this had been plus, would it have been necessary?
Nope.
Yeah, not really, right? But it's not a sum quotient. It's a difference quotient. You're subtracting, right? This has got to be subtracting here because we're taking a difference in the y values, right? You don't add your y2 plus y1. You do y2 minus y1. So that this negative essentially, will affect both of these terms, and so these square brackets here are there. Like, do need to be there? Those are actually necessary. So so I always put parentheses or brackets. The only reason I use brackets instead of parentheses is just to keep it visually organized, I think. I also like to use different colors for the same reason. You should feel totally free and welcome to use different colors. If you come to class and to quizzes and work on your assignments with a bunch of colored pencils or something, like, awesome, great. Like, I think that's awesome. I totally encourage that. That's why I do it. It's because I think it just really like keeps things organized when you use different colors for different things. But anyway, yeah, I like to put way more parentheses, not way more, but a bit more parentheses than I really need to, because it's safe. It's always better to use more parentheses than less parentheses, almost. Okay, so let's move on here and see what we get. So what we've got to do now is like get in here to our numerator and start just simplifying that whole numerator up. We've got to make sure that it's you got to sort of expand any squaring and like combine like terms and that sort of thing. So up on the left side over here, the first thing I'm going to do is square 3 plus delta x. Got to be careful to do this correctly. I'm going to get 3 squared plus 2 times 3 times delta x, and then plus delta x squared. Okay, so this 2 times 3 is what I have right there. Okay, so that's the like that's the a plus b squared is a squared plus 2ab plus b squared. If you're not totally comfortable using that shortcut, please write out 3 plus delta x times 3 plus delta x and FOIL it, okay, to avoid making a mistake there. So that's what I get from squaring. And then I have to distribute this 4 over here, right? So I get 4 times 3. And I'm just going to write it out like that first, and then plus 4 delta x. And that'll simplify a little bit in the next step. Oops. Okay, and then down here, I'm going to get minus, and then here I can do 3 squared plus 4 times 3. This is going to be 9 plus 12. So I can do minus 9 minus 12. Or, you know, I could have just done, instead of distributing the negative, I guess I could just do like 9 plus 12, which is 21, and then just subtract 21. 9 plus 12, 21. Yeah. But I'm going to do minus 9 minus 12. Okay. So going back in here, I have a 9 there. I have a 4 times 3 is 12. So let's do that. That's 12. Over here, we have a 2 times 3 delta x, right? That's from the 2ab, right? So I guess I'll just do the 2 times 3 right there. That's 6, right? And in my denominator, I still just have delta x. Okay, so now this is the beautiful moment where a bunch of things cancel out. Right, I have a, let's see, I have a plus 9 minus 9. It's going to cancel out. I have a plus 12 minus 12, which is going to cancel out. Right? And then I can also combine some like terms. I have a 6 delta x here, and I have a 4 delta x there. So what I have now is just delta x squared plus 10 delta x all over delta x. And look how much simpler this limit has become, right? Oh, shoot. Yeah. Okay. Okay. Shoot. Everybody, I forgot to do something. I forgot to do something. All right. Folks, finish up the last couple steps on here. I got to do something real quick. I got to send an email. Okay. And then I'll be right back with you. Okay, just a second. Okay, so this is pretty nice and easy now, because all we need to do is factor and cancel. Never forget to factor before canceling. So there we go. If you factor out a delta x from the terms in the numerator, then you can cancel it. Be careful that you don't cancel before factoring. If you try to cancel first, you might get in trouble. So like right here, for example, that is a really common mistake, is to try to cancel those delta x's. Don't do that, because those delta x's don't cancel out. These ones do cancel out, though. This is totally fine. A-okay. What's the difference? Why is it okay to cancel those, but it is not okay to cancel these?
Because you have to factor out the delta x first so that it cancels out both of them. Because if you were to just do like where you say no, it's not taking the whole delta x, because you distribute. You have to undistribute to cancel everything correctly.
We do have to undistribute. Yep, we always so undistribute, factor out delta x. Yep, we gotta do that first. Why though?
The delta x in the first one is still inside of a term.
That's true. It's locked inside of one of these terms. There's two terms, which is, I'm glad you brought up the word terms, right? What is it that you cancel when you're canceling something from the numerator and denominator of a fraction? What are you canceling, and why can you cancel them? You're canceling what we call common factors.
Like terms, isn't it?
Is that right? What's that, Vanessa?
Like terms.
I wouldn't use the word like terms, because first of all, terms is about adding things. Maybe you could call them like factors, common factors. Like terms are that's a phrase used more often when you're combining like terms, like what we did up here, like six delta x and 4 delta x are like terms, right? They're like terms because they can be combined. They have the same variables. But the delta x is not a like term, it's a common factor. So let me back up a little bit here to before I did this canceling. There we go. We don't want to do that. Yes, we want to make sure we factor out, because the things that you're canceling, like from the numerator and denominator of a fraction, need to be the factors, like need to be a factor of the numerator and a factor of the denominator. Until you have factored it out and written it as delta x times everything else, delta x times everything else, not just delta x times x plus some other stuff, right? Like it can't be a factor inside one term among many. It has to be a factor of the entire numerator, which is why you've got to factor first and before you cancel. Yeah, okay. So I just felt the need to do that review. So now we have the limit as delta x goes to 0 of delta x plus 10. And this is just going to be 0 plus 10, which is 10. That's our final answer there. It's 10. Now let's double check. How can we double check? How can we check to see if our answer here is correct? Well, one way is to go over to, wait a second, what just happened? We can go to Desmos and we can graph it. Did that sound properly? It did. Okay, good. Okay, so this function was x squared plus 4x, and we were doing a equals 3, right? Okay, so I can graph the point a comma f of a so that I can see the point on the graph. There's the point on the graph, a comma f of a, right? A is where a is 3. We don't allow that to change. Okay, so that point right there, that's the point where I want to do a tangent line. And what I just found out, right, we just found the slope of the tangent line, 10. That's what we just found out, right? So now one way we can check it is to graph that tangent line. How do you graph a tangent line? Well, we need to use the, we need to get an equation for the line. We want a line. So actually, let me get back over here and I'll kind of put this on the main page here. Let's flatten this. Okay. Now, a tangent line equation has to pass through the point, passes through a comma f of a, which for our purposes here is going to be 3 comma f of 3. What's f of 3? 3 squared plus 4 times 3, that was 9 plus 12, that's 21. If I do my arithmetic right. 3 comma 21 is our point. So that's one of the point, that's the point the tangent line has to pass through. And then the slope is f prime of 3, which we just found is equal to 10. So these are the two key pieces of information. We need the point and we need the slope. Now, what we can use here, if we have a point and a slope, we can use the point slope form of a line equation, which is y minus y particular, y minus a particular y equals the slope times x minus the particular x. That look familiar? From algebra, this is the point slope form of a line. So if we can specify this at least a little more, we can say y minus f of a, because f of a is going to be the particular y value, equals the slope, which is f prime of a, times x minus a. And this right here is the general formula for the equation of a tangent line. This is something you can memorize if you want to. It's pretty nice. Y minus f of a equals f prime of a times x minus a, tangent line. So for our case here, it's going to be y minus 21 equals 10 times x minus 3. So let's graph that in Desmos. Oops, put that there. So I'm graphing that y minus 21 equals 10. Oops. 10 times x minus 3. And that line, let's make it a different color from the original graph. Let's make the original graph like black. And the point can be a red point. Okay, there we go. So that should look pretty much like a tangent line. Does that look like a tangent line? Does it look right? I'm going to change the scale here. And I'm just messing with my y-axis here on my touch screen. If you don't have a touch screen, you can mess with the y-axis by just changing these boundaries up here in the like little graph settings over here. But if you have a touch screen, you just grab the axis and you just pull it together or whatever. Yeah, so that looks a little better. That looks like it should, doesn't it? So that's one way that you can check to see if your answer is reasonable, is by graphing the tangent line and then looking at it and, you know, asking, does it look the way it's supposed to look? Okay. We have like 5 minutes. Let's look at another example. What if you had f of x equals the square root of x? And let's take a equals 4. So we have something that's a perfect square. Well, then we would be doing, for f prime of a, right, for our derivative, we would be doing the limit as delta x approaches 0 of f of 4 plus delta x minus f of 4 all over delta x, like that. And then you've got your, 4 plus delta x, which needs to go in here, right? So what I'm going to do is write the square root of blank minus the square root of blank. And in this first blank, I put 4 plus delta x. And in this second blank, I'll put 4. Like that. Right? And that's all over delta x. Oh, does this look sort of familiar? I'm going to put a dot, dot, dot to indicate that we can continue working on that. Another way to set this up is limit as x approaches 4, and we'll do f of x minus f of 4 all over x minus 4. This is the other of the two ways to define it. So like this was actually like the way I called number 1, and this was the way I called number 2. But I told you that this is more common. Remember, I put a star by the second one. So this is the alternative way. And so here we have the square root of x minus the square root of 4 all over x minus 4, or in other words, square root of x minus 2 all over x minus 4. Like that. So I ask again, do these look familiar?
Yes.
Yeah, I've been having you guys practice solving limits like this since like day 1, right? Or day 2, maybe. I've been making you guys practice this algebra, the algebra involved in solving these limits. This is what are you going to do here, everybody? What am I going to use here? What's the strategy for simplifying this expression?
Multiply by the conjugate.
That's right. Multiply by the conjugate. Right. Okay. So this is where we'll go ahead and end for today. You guys can finish this if you want, and we can go over it next week. I'm going to get exercise set 3 written up today and put out to you guys as soon as I can. Exercise set 3 is going to be due Wednesday of next week. Okay, so I'll get that to you ASAP so you can get started working on it. But it's going to involve, it's definitely going to involve some of this derivative stuff. Okay. Mostly this derivative stuff. All right. Have a great weekend, everybody. I'll see you Monday.